Hi YouTubers. We're conducting tests with various morphologies of graphite felt and fiber. And here, using this inexpensive power supply, the trade name is Nice-Power. You can find them on Amazon, US dollars, about $35, $36, $35, $36 plus postage. Very good, inexpensive power supply. You can do constant voltage or constant current. You can see we're running it now at CC. And at 6.3 volts, we're pushing through 500 milliamps. The circuit is an approximately 5 watt rated LED as electronic load. And I don't run the little DC motors. I really should, but I'm going to have to put a small capacitor in there to silence it when I run this in the lab, because these old things can get noisy. But for now, the LED, which is fine. The circuit, and I'm using a breadboard. I usually would not go above 750 milliamps with a breadboard. Then I'd go to a printed circuit board. But very simple setup. Interestingly enough, this plastic container holds, it's commercially available, it holds dental floss, toothpicks, plastic dental floss. The company is based in Switzerland. They sell in the United States, and I would assume in many other countries. And these plastic containers are very good because we immerse it in dimethylformiimide solvent. We work with supercaps, and they don't dissolve or decompose, even after soaking for a week. So anyway, here's one of these plastic containers. We ran an infrared on it. I have yet to look it up and try to track down what the plastic is, and I also contacted the company, and I'll keep you posted on that. So I have a piece of commercial graphite felt. Usually it's about 5 to 8 ohms per centimeter with a multimeter, which is fine for our purposes. And that's in the case. It's what I call a dry circuit, no electrolyte or solvent in the felt pad. Just want to see how it performs for 7 to 12 days at constant current. See if there's any change in resistance. And initially, it was at 6.1 volts, half an amp, and I let it go for about an hour and a half. And then I attached into the circuit, I included a AA cylinder in a cradle, and that's packed somewhat loosely with graphite twine. And we haven't done any nickel plating on these morphologies, but we will. And I just got the twine in recently, and I could see some applications with this in terms of the flexibility. And of course, when you nickel plate the graphite, the surface will become a little harder, and it could possibly break. We've seen that happen. And what we're doing right now is simply examining the samples of graphite. For example, I have a sample right now soaking in oxone, OXONE, which is a commercially available, that's the trade name, for potassium peroxymonosulfate, pretty good oxidizing agent. And we have it in 20% oxone mass, 20% solution in water. And I'll let it soak for 2 days, and I'm already seeing a little bit of peeling on it. So there's a lot of interesting things we want to do here. We also want to sonicate, ultrasonicate the graphite forms. And that's where we're at right now. Now, when I incorporated the graphite twine into the circuit, it went up to 6.3, so a little bit more resistance. So we'll let this run probably for a week. then I will take them. We'll do scanning electron microscopic examinations, but then we're going to sonicate, treat with oxidizing agent, and ultrasonicate for perhaps 15 minutes, just to see how the graphite performs before we actually utilize it as a potential electrode in supercaps. I work with undergrads, and home researchers may be interested in this too. And if you're teaching in a college and you're on a tight budget, these power supplies are very worthwhile in case you need to pick up 5 or 7 or 10 of them for use in a class. I will post the company that sells these power supplies. Thank you very much for watching. We'll keep you posted on our research. Bye for now.